class!
Today we're going to start our acids and base chapter. So up until this point, I've been defining acids as they start with hydrogen and bases end in OH. And that definition that I've been giving you is the Arrhenius definition of acids and bases. So based on Arrhenius's definition, an acid is a substance that when you dissolve it in water creates H plus ions. So things like hydrochloric acid, sulfuric acid, and phosphoric acid. Bases are going to be defined as when we dissolve them in water, they tend to increase your hydroxide ions. So things like sodium hydroxide and calcium hydroxide. However, while this definition is very useful, it does have limitations because it restricts things to aqueous solutions. Around the same time, though, two scientists, Johannes Bronsted and Thomas Lowry, were independently proposing their own definitions. And so we put their definition together to make the Bronsted-Lowry definition of acids and bases. Their concept is based on the fact that acid-base reactions involve just a transfer of a hydrogen ion, or in other words, a proton, from one substance to another. And this is actually very beneficial because it allows us to define acids and bases in other states of matter besides a solution. So we can apply this to solids, liquids, and gases. So if we're going to look at the definition of acids and bases, we can use the following reaction. Hydrochloric acid dissolves in water. So we have HCl reacting with water. What we're going to see is that the hydrochloric acid is going to lose a hydrogen and make chlorine negative. Now, it's going to change from a neutral charge to a negative charge because it's losing a positive ion. So it becomes more negative. Well, where does that H go? Well, what happens is that H is actually going to attach to water. Instead of having H2O, it's going to be H3O. Now, when you move and attach a hydrogen, which is positively charged, you're going to become more positive. So it goes from neutral to a positive one. In this example reaction, HCl tends to act as an acid because it's donating a proton or a hydrogen, and H2O is going to act as a base because it accepts a proton or a hydrogen. Now, one thing to know about acid-base reactions is that acid-base reactions always work together because something has to donate a proton and something else has to accept that proton. So note that substances can only function as an acid if you have something else reacting as a base to take that proton, and vice versa. Now, some substances can act as an acid in one reaction and a base in another. We call these substances that are able to act as either an acid or a base as amphiprotic. Things that can be amphiprotic are things like water. We have a bicarbonate ion, which is HCO3 negative 1, or bisulfate, which is HSO4 negative 1, are common amphiprotic molecules. Amphiprotic substances act as a base, typically when it's with something that's extremely acidic, and it tends to act as an acid with something that is extremely basic. Here's an example where we have bicarbonate and water and how each one can act as either an acid or a base. If I had a bicarbonate and it was acting in a base, that means it's going to accept a hydrogen from water. So one of these hydrogens from water are going to go over and join with our bicarbonate. Notice now I have two hydrogen here. Because I gained a positive charge, I went from a negative to neutral because negative 1 plus 1 is 0. Here I have water. It lost a hydrogen, so now I just have one oxygen and one hydrogen. Because I lost a positive charge, it became more negative. The other way is going to work here on the bottom. If HCO3 negative acts as an acid, what's going to happen is this hydrogen is now going to go to water. So I'm left with CO3 because I'm losing a positive charge. Negative 1 minus 1 gives me a negative 2 charge there. Over here, my water accepted a hydrogen, which is how I got to 3 hydrogen right here. and I'm accepting a positive charge, which is why I add a positive charge up here on hydronium. I really like this image because it's also going to bring into account something I'm going to define on the next slide called a conjugate acid and a conjugate base. One thing to note about these is anytime you have an acid and a base, the products are typically called conjugate acids and conjugate bases. So here, this base has a conjugate acid, and this acid has a conjugate base. Typically, acids and bases are on the left side of the equation, and our conjugate acids and bases are on the right. So let's define conjugate acid-base pairs. Again, this is an acid and a base, such as HX, and X just stands for any ion, anion. So it could be F -1, CO3 -1, any negative ion, and X negative. That differ only in the presence or absence of a proton. So I've bolded these next two sentences, basically stating every acid is going to have your conjugate base, and this conjugate base is formed by removing a proton from the acid. Every base is going to have a conjugate acid, and the conjugate acid is formed by adding a proton to the base. So we're going to look through several examples, and our first one says, what is the conjugate base of all of the following substances? So one thing to note is that if we have a conjugate base, this is formed because all these substances are acids. And acids tend to donate hydrogens or H pluses. So if I was going to give the base, I need to get rid of a hydrogen off of these. So here, if I get rid of one hydrogen, I'm left with ClO4. But because I got rid of a positive charge, this is going to affect my charge up here. So 0 minus 1 gives this a -1. On the next example, we want to get rid of one of these hydrogens. So now I just have one hydrogen and a sulfur. I have a 0 neutral charge, but I got rid of a positive, so 0 minus 1 gives this a -1 charge. pH4 with a +1. If I have this, I'm going to get rid of one of these hydrogen to make this 3, so pH3. I had a +1 minus, I got rid of a proton, so that gives me a 0 charge. And then here I'm going to get rid of one of these hydrogen, so I have CO3. I originally had a -1 charge, but I'm subtracting a positive charge from it, so this gets me down to -2. If you have questions on any of these examples, please make sure that you guys come up and ask. For if I was going the opposite way, what is the conjugate acid of all of the following? If you have a conjugate acid, that means that these are all typically bases, and they are formed by accepting a hydrogen ion. So that means we're going to add hydrogen to all of these. So if I add hydrogen to CN, I typically get HCN. Now I'm adding in a positive charge, so -1 plus 1 gives me a charge of 0. If I have a sulfate ion and I add a hydrogen to it, HSO4, I'm adding in a positive charge, so -2 plus 1 gives me a -1. We've worked with water before, so if I add a hydrogen to water, I get H3O. And notice it's going to go to a positive charge because I'm adding a proton. Here I'm going to add a hydrogen. So now I have 2 hydrogen, CO3. I'm going to add a positive, so -1 plus 1 gives me 0 charge. Here I'm going to add a hydrogen, SO3, -1 plus 1 gives me a neutral charge. F, got to add my hydrogen. Same thing here, -1 plus a proton gives me a neutral charge. And then over here, HPO4, we have a -3 charge plus a proton, which leaves this compound with a -2. Again, just like the ones above, if you have questions, please make sure that you ask. The last set of examples I'm going to give is I'm going to give you an equation, and I want you to be able to identify the acids and bases on the left. So acids/bases are going to be on the left. And then I want you to be able to identify the conjugate acid and conjugate bases on the right. You have to make sure you pay attention to kind of what's going on. So here I have HCl. Notice Cl on the right has lost a hydrogen. So if it loses a hydrogen, that is going to be an acid. That means Cl will be my conjugate base because they are opposites. If HCl is my acid because it's donating, NH3 will be my base because we can see that it's accepting that hydrogen. We get another hydrogen over here. That means my NH4 on the other side would be my conjugate acid. If I look at the second example over here, we have to see what's happening to PO4 3 negative. If we find a PO over here, we're going to see that PO4 actually gained a hydrogen from HNO3, or nitric acid. So since PO4 is accepting a hydrogen, this is considered a base. That means my PO4 over here must be the conjugate acid. If this one is the base, my other reactant must be the acid, and the corresponding one would be the conjugate base. On our last example, we have to see what's happening here. We have HSO4 negative 1. If we find SO4, we're going to notice on the right that it lost a hydrogen, so it gave it away. That's going to make that an acid. That means the corresponding product would be the conjugate base. Since PO4 3 negative accepted that hydrogen, it's going to be a base, and the corresponding product would be the conjugate acid. That's the end of today's lesson. If you have any questions, please make sure that you ask, and I hope you guys have a great day.